Good morning, it's Chris Potter. It's June 1st, 2017. Sharing an article from Astronomy magazine, or astronomy.com rather. Merging white dwarfs may create most of our galaxy's antimatter, written by Alison Klesman, published on Monday, May 22nd, 2017. The discovery helps to rule out more exotic sources of antimatter, such as dark matter. The following illustration shows two white dwarfs in a binary system. They can spiral downward towards each other and merge, setting off a supernova event that triggers the creation of material that will decay into antimatter over time. More than 4 decades ago, astronomers discovered the first gamma ray emission coming from outside the solar system. This high energy signal is associated with the destruction of roughly 10 to the 43rd power positrons, a type of antimatter, each second. Despite extensive follow-up, astronomers today are still looking for the exact source or sources for that emission, which could run the gamut from mundane, natural processes in a star's life to exotic, dark matter origins. Recently, a group of astronomers has determined that positrons resulting from white dwarf mergers could contribute significantly to the signal that we see. The emission associated with galactic positron annihilation, oh, what a cool set of words, occurs when a positron meets its counterpart, an electron, destroying both particles in the process. Thus, this emission requires a ready source of antimatter, which has remained mysterious ever since its initial detection. Measurements suggest that the signal is nearly 1.5 times higher in the bulge, or central regions of our Milky Way, than in the arms. This particular aspect of the emission has led to the development of several models that speculate an overabundance of positrons in this area could be due to processes related to dark matter or our galaxy's central supermassive black hole. However, many astronomers are still searching for less exotic ways the positrons we're seeing undergo annihilation could be produced. In a published paper on May 2nd in Nature Astronomy, first author Ronald M. Crocker of the Research School of Astronomy and Astrophysics at Australian National University and his co-authors examine a possible stellar source of galactic positrons that could be responsible for that signal of white dwarf mergers. White dwarfs are the remnant cores of sun-like stars left behind after the star runs out of fuel and dies. If two low-mass stars, roughly between about 1.4 and 2 times the mass of our sun, circle each other in a binary system, they can interact via a process called mass transfer, where gas from the stars is exchanged. Oh, very interesting, boo. The end result is 2 white dwarfs that may eventually merge, and that merger can result in the production of radioactive isotopes that decay into positrons. There are several clues that have led Crocker and his authors, or co-authors rather, to this conclusion. The ratio of the signal's strength in the bulge and arms is similar to the ratio of the stellar mass, essentially the number of stars, in these two structures as well. This led the astronomers to consider that the positron production could be related to an older stellar population, such as white dwarfs. Additionally, by looking at the processes that produce positrons through radioactive decay, they determined that the decay of 44 Ti into positrons is the most likely source. However, this material is not produced in sufficient amounts in most core collapse supernova, which occur when a massive star reaches the end of its life. While supernova triggered by the merger of 2 white dwarfs are much rarer, these events should produce more 44 Ti per merger, which then would decay and produce the number of positrons required to create the emission line from their subsequent annihilation. The current resolution of instruments used to study this emission is not high enough to find point sources such as individual supernova remnants in the bulge. Thus, more precise measurements and computer simulations will be needed to determine the positron production rates from such events. The authors also state that white dwarf mergers are likely not the only source of antimatter in our galaxy, which still includes contributions from massive stars and black holes, even if dark matter is eventually ruled out as a viable source for this emission. Thanks for watching and subscribing. I'll put the link below. Chris Potter, have a wonderful day, and take care, Bo.